Ladies and gentlemen, your class recording has started. So today, as I mentioned to you earlier, up until this point in this unit, we have dealt with chemical reactions from a qualitative standpoint, where we're just talking about what are the reactants, what are the products, do we have enough reactants, do we have enough products to balance it, etc., etc., etc. Today, we start getting into the introductory ideas of something that we call stoichiometry, which is just a fun word to say. Stoichiometry, like its definition states, which is also the first part of your outline, right? Mass and quantity relationships among reactants and products in a chemical reaction. So this week, we now start taking a look at not only what are the reactants and the products, but if we know how much of a reactant we have, we can then predict how much of a product we should get out of that reaction, which is important when you're doing things like industrial chemistry and making, if you make chemicals for a living, you want to know about how much you start with and how much you should end with, so you know how much to buy and how much you're going to make, blah, 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 right? That's where we start this. All right, so stoichiometry. Calculation of quantities of substances involved in a chemical reaction. Like we said, we put numbers on this. Now it's not just what are the reactants and what are the products, how much of this reactant gives us how much of that product. And if we know we start with this much reactant, how much product should we get? Or if we know we need to make a certain amount of product, how much reactants do we need to start with? The key factor that helps us determine these numerical relationships or these mass relationships is the chemical equation, specifically the coefficients of the chemical equation. The coefficients not only are there to balance out the equation, right? Make sure that we have the same amount of mass at the beginning as we do at the end. It also indicates a ratio of reactants to products. And we will use that ratio to figure out how much of something we start with versus how much something we end with. Good there? For instance, there is a chemical equation that shows the synthesis of a compound that we call ammonia. So ammonia is formed from nitrogen and hydrogen. Nitrogen and hydrogen are both diatomic, so we have to have them as N2 and H2. Ammonia is NH3. You could go through pretty easily, and I think I actually gave it to you already, right? But if you go through, you can figure out that this is the balanced chemical equation for the production of ammonia. Now, if we look and if we did an atom inventory, you would see that there's the same amount of nitrogen atoms as there are in the reactants as there are in the products. So same amount of nitrogen in the reactants, same amount of hydrogen in the reactants as there are in the products. Atoms. But when we look at the equation, nitrogen doesn't exist as two individual atoms. Remember the subscript indicating that those two atoms are bonded together. So this is a nitrogen molecule, right? And these are hydrogen molecules. So we use the coefficients to count up the number of reactant atoms and product atoms, but we can use the coefficients to look at the ratios. For example, this equation is telling us that we need one nitrogen molecule and 3 hydrogen molecules to make 2 ammonia molecules. So yes, the coefficients make the number of atoms balance, but because the atoms are rearranged in the process of the chemical reaction, we may end up with a different number of molecules, or a different number of groups of atoms than we started with. In the reactants of this reaction, we have 2 nitrogen atoms and 6 hydrogen atoms. But we have 1 nitrogen molecule and 3 hydrogen molecules. And then in the products of this reaction, we have 2 nitrogen atoms and 6 hydrogen atoms, just like we started with, but they're rearranged. So now instead of being 4 small molecules, they're 2 bigger molecules. And that's the gist of a synthesis reaction anyway. Okay? Good there. Now, counting out 1 molecule of nitrogen and 3 molecules of hydrogen to make 2 molecules of ammonia is hard. Molecules are really small. We can't do that. We can't get 1 individual molecule of nitrogen and 1 molecule of hydrogen to give us 2 molecules of ammonia. Not possible for us. But we talked about the idea that we can look at ratios in the big world through this number. Right? Does that number look familiar? Hopefully, yes, maybe. Right? Remember what it's called? Anybody? Mark? Avogadro's number, right? Or Avogadro's constant. That number is significant. Why? Why is that number significant? What does it tell us, Andy?
It tells us the amount of atoms in 1 mole of a substance.
It tells us the amount of atoms in 1 mole, but we said that we've used it in the context of atoms, right? But really, it tells us the amount of anything in 1 mole, because mole is not a specific counting value to atoms. It applies to anything. So it tells us how many atoms are in a mole, but it also tells us how many molecules are in a mole. So, regardless of the fact that nitrogens are bigger than hydrogens, and regardless of the fact that ammonias are bigger than either one of them to begin with, we can use this value to make an assumption that yes, this equation shows us 1 molecule of nitrogen and 3 molecules of hydrogen give us 2 molecules of ammonia, but it also can be used to show us that 1 mole of nitrogen plus 3 moles of hydrogen will give us 2 moles of ammonia. And moles are easier for us to measure. What factor or what value do we use in order to measure a mole of something? Andy?
Atomic mass units.
You're on the right track, but let's say it properly. Atomic mass units applies to an individual atom and how it compares to carbon-12. When we take it to this value, we don't call that number the average atomic mass. What do we call it? Help?
Yeah.
What do we call it when we're talking about in terms of this? Not the atomic mass. Now we call it the what? The molar mass, right? Numerically, where do we get that number from?
Average atomic mass.
The periodic table, right? That number on the periodic table. But now we call it the molar mass. Okay? And these values, when we talk about them in terms of moles, are much easier for us to measure. All right. Next page, method, right? Stoichiometry problems are conversion problems. It helps if we know what we're looking for. That's going to be the first thing we should determine. Once we have figured out what we're looking for, right, is this next? No. Never mind. Is it on the next page? All right, here. Just watch this part here, and then we'll get to doing it in a second, right? It helps for us to determine what we're looking for first. Then, what did they give us to work with, right? What did they tell us we have to start with? Once we've done that, what's my plan? Your plan is a conversion factor problem. Stoichiometry problems are conversion problems. A little bit different than what we've done up until this point, but they're just conversion problems. So we're going to make a plan. We're going to make our conversion factors, right? Time, sign, fraction, bar. We're going to fill in the units that we're looking to get rid of, the units that we're looking to go to, and then fill in the numbers. Once we do that, now just do it, right? Sometimes you might refer to this as plug and chug, right? Put it in your calculator, chug it through, get the answer. Okay? And then make sure we end up with the correct number of units, the correct number of significant digits, certain, uncertain digits. We go from there. Okay? Good? All right. The first type of problem we're going to start with are mole-mole calculations. They're the easiest ones. You'll see that here in just a second. So, mole-mole calculations. If we're given the moles of one reactant or product, we're going to calculate the moles that is required or produced of another reactant product. I know that's pretty wordy, but all that means is if I give you a number of one thing in that equation, you can figure out the number of any other thing in that equation, right? We don't have to go reactants to products. We can go backwards products to reactants. Either way. Steps to follow. First thing, we have to have a balanced chemical equation. That's the first step in any stoichiometry problem. The balancing of the equation gives us the ability to compare one part of that reaction to another part of the reaction. Once we've figured out the balanced chemical equation, we're going to write the moles of whichever number we're given, whether it's a reactant, whether it's a product, whatever it might be. And then we're going to use the mole ratio as a conversion factor to calculate the amount of moles that we want to end up with. And those steps are listed there in your outline, right? So, here's our first problem. It's an example. It's question number, or it's letter number C in your outline down on the first page. So it says, in the space station, carbon dioxide exhaled by astronauts can be removed by a reaction with lithium hydroxide. This reaction produces lithium carbonate and liquid water, which could be useful, right? So we can use it in other parts of the station. So 2 questions. It says, how many moles of lithium hydroxide would be needed to remove 20 moles of carbon dioxide, which is the average daily amount that's exhaled by a human? And then, how many moles of water are produced from this reaction? So, let's go here. I'm going to take this, I'm going to put it on a separate page so that we can write on it, and then we'll go from there. All right, so, steps to follow. Said the first step that we have to do in solving any stoichiometry problem is what? Say again? What are you looking for, right? So let's start with this one right here, right? What are you looking for? This is like number 1 on your sheet, or on your page there. What are you looking for? What is this question asking you to solve for? Andy, go ahead.
The amount of lithium hydroxide that we
Okay,
needed.
so we need how many moles of lithium hydroxide? I'll do the formulas for you so you don't have to worry about those. So that's what we're looking for in this problem. Like I said, this is number 1 on your outline down at the bottom of the first page. Letter C, number 1, we're doing it right now. Okay? All right, so in this first reaction, number 1, we know what we're looking for. What else did they give us to work with?
20 moles of carbon dioxide.
We know that we have to get rid of 20 moles of carbon dioxide, right? We know that that's how much a human exhales each day. And yes, I know that there's more than one person on the space station, so we would have to multiply that factor. But if we calculate it on a per person basis, then we can just multiply by 5 or however many people are on the space station, and we're good. All right, so we figured out what we needed, and we figured out what we have to work with. Okay? Now we got to make a plan. Our plan consists of 3 steps. The first part of our step of making a plan involves what? I told you that one of the most important things as far as a stoichiometry problem is concerned is what do we need to determine first? This one actually is written in your outline. Letter B, number 1, what's the first thing that we have to do? Balanced equation, okay? So it says, carbon dioxide exhaled by astronauts can be removed by a reaction with lithium hydroxide. This reaction produces lithium carbonate and liquid water. From that description, you should be able at least to tell me what are the reactants of this reaction and what are the products of this reaction. Okay? Think about it. If you can't figure, if you don't have it in your head, take 10 seconds and think about what are the reactants and what are the products. All right, what do we start this reaction with? What are our reactants for this reaction? Nick, go ahead.
Carbon dioxide, lithium hydroxide.
Okay, so Nick, you know what the formula for carbon dioxide is, right? It's what?
CO2.
Okay, so CO2 plus, we said the other reactant is what?
Lithium hydroxide.
And I just told you right here that your formula for lithium hydroxide looks like this. Okay? Based on the charge of lithium, where it is on the periodic table, based on hydroxide's charge, -1, that's the formula. Okay? And then, 2 products for this reaction. Nick, do you want to keep going? What are the 2 products of this reaction?
Lithium carbonate.
Lithium carbonate and water, right? So you know the formula for water, right?
H2O.
H2O. Okay? And then, lithium carbonate. Lithium has a +1 charge. Carbonate, there's your carbonate ion, it has a -2 charge, so the formula for lithium carbonate looks like that. Okay? Again, I will not ask you to figure out the products like that of a reaction. I will give you the balanced equation in terms of the stoichiometry problem. Sorry, I will give you the equation, not necessarily a balanced equation. So, is this equation balanced? As it is written right now? It is not, okay? So we need to do a couple of things in order to balance it out. Go ahead and balance this equation. All right, so this one's pretty easy to balance actually, right? It just requires 1 coefficient. You got to put a 2 in front of the lithium hydroxide and go from there. Okay? All right, so we balanced the equation. Now, the next part of our plan. Write the moles of whichever one we were given. So we were given that we starting this reaction with 20 moles of carbon dioxide. It becomes much more important in these problems to make sure that we are writing the formulas, because we'll see here in a second that when we're talking about one formula or the other formula, it becomes, we need to know which one we're talking about. So make sure we're writing formulas along with our units. So we start with 20 moles of carbon dioxide. Then, this is a conversion problem. So, time sign, fraction bar. Okay? Our conversion factor has to do 2 things. It has to cancel units and it has to leave us with units that we're looking for. So what unit has to go on the bottom of this conversion factor? Andy, go ahead.
Moles.
Of?
Lithium hydroxide.
This has to go on the bottom. Moles of carbon dioxide, right? Because that's what we're trying to get rid of. This problem, we want to end up with moles hydroxide. That's what it asked us for. Okay? Let's see if we can get this done real quick. This conversion factor here we call the mole ratio. The values for the mole ratio come from our coefficients. So, if we look at their equation, 2 is the coefficient in front of lithium hydroxide. And then what's the coefficient in front of carbon dioxide? Just 1. This value here is called the mole ratio. And that's how we solve this problem. Okay? We will pick up on this tomorrow. That packet that I gave you actually has your homework for the next 3 days in it. So we'll do some stuff in class. I'd like you to finish it up for homework. The one that's labeled mole is where we're going to start. Okay, so yes, no. Say again? Finish it up. Yeah, need to get it done today, great, but finish it up. All right.